Hello everyone, welcome to our discovery of our second conic section. I've built this nice Desmos animation for you for us to discover this conic section. If you want, I have this animation linked to our WAMAP page. So if you want to just go ahead and stop watching this, you want to click on this animation and kind of follow these directions to discover it on your own, you can definitely do that. If not, I'm going to kind of walk you through the animation. But in our first conic section, what we did is we defined a shape directly from just a dot. We said we had this dot which we called the center, and our shape was defined to be the set of all points that are a fixed distance from this dot. So if our center was, let's say, at the point 0, 4, and we wanted to find the set of all points that are a distance 3 away from the point 0, 4, we can go out 3 units, finding the set of all points that are 3 units away from 4, we'd get a nice circle. So that was our first conic section. But instead of defining a shape just from a dot and a fixed distance, we're actually going to define this new conic section from a line and a dot. The shape that we are going to create here is going to be completely defined from a line and a dot. How fun. Okay, so the line is what we call the directrix. Now, when you're working with this animation, you can just go ahead and click on this open circle here on the left, and that should turn on the feature I want to show you. So here is this line. Right now it's a horizontal line. We call this the directrix. It doesn't have to be a horizontal line. It could also be a vertical line, but for this animation it'll be a horizontal line. So we have this line which we call the directrix and a dot which we call the focus. So we have this other dot here we call the focus. Now the shape that we're going to create is going to be completely defined from this line and this dot, or from the directrix and the focus. Okay, before we start talking about the shape, we'll actually find that the shape will completely depend on how far apart the focus and the directrix are from one another. So we're going to define a parameter that'll tell us the distance from the directrix to the focus. Now, for convenience, I'm going to put the origin, or the origin will be halfway between the focus and the directrix. And now to come up with a parameter that will tell us the distance from the directrix to the focus, I'm going to call this parameter p. And actually I'm going to define this parameter p to not be the distance from the directrix to the focus, but I'm actually going to define p to be the distance, in this case, from the origin to our focus. So I'll go ahead and turn this on here. So this is our distance p. So right now from the origin to the focus is a distance of 2.7. But since we put the origin halfway between the directrix and the focus, the distance from the origin to the directrix will also be p. So actually the distance between the focus and the directrix will actually be 2p. Now we can change this distance by using the slider down here. Now you could go ahead and hit play here to see it animate, but I don't know, it's much easier in this case to just kind of drag the slider back and forth. A good thing to notice here that is, if p is positive, the way I've defined it, if p is positive, that means that the focus will be above the directrix. If p is negative, the focus will be below the directrix. Okay. So right now, let's put p at 4. So that means that the distance from the origin to the focus is 4. The distance from the origin to the directrix will also be 4. So the distance from the focus to the directrix will be 2p, or will be 8 in this case. Okay, now what are we going to do with this line and the dot? How are we going to define this shape? Okay, so the way we're going to define the shape is we're going to define our shape to be the set of all points such that the distance from a point on the shape to the focus will be the same as the distance from the shape to the directrix. Okay, what do I mean by that? Let me give you an example of a point that'll be on the shape, and then we're actually going to define a bunch of them to draw this shape. So I'm going to say that actually the origin will be on this shape. Okay, why will this point here be on the shape? Well, the distance from the origin to the focus is 4, but also the distance from the origin to the directrix will be 4. So this point will be on our shape because the distance from it to the focus is the same from it to the directrix. Another point that will actually be on the shape will be this point right here. The point 84 will be on that shape because the distance from the focus to this point, if we count, will be what? 1, 2, 3, 4, 5, 6, 7, 8. And the distance from this point to the directrix, 1, 2, 3, 4, 5, 6, 7, 8, will also be 8. So this point here will be on our shape. Likewise, this point here will also be on our shape. Okay, so with this definition, how could we draw this shape? Let's say you were actually doing this at home and you wanted to create the set of points that are an equidistance from the dot, the focus, as from this line, the directrix. How could you do this? Well, you would draw your dot and you would draw your line. And then what you might do is you might take a string. Let's say you take a string of length 4. You start it at the focus, and then what you'll do is you'll draw a circle around the focus. So that's what I have right here. So we have this. Oh, let's zoom in a little bit. Okay, so let's say we have a distance of 4. So this circle right here, all these purple points, are all the points that are a distance 4 away from the focus. So now what we want to do is we want to find a point that's on this circle such that the distance from this circle to the directrix will also be 4. So we can look at that distance right here. Oh, just a note here that you can change this circle right here. You can change the radius with this slider. And at the angle at kind of which this line is pointing, you can change with this A. So it's just going to rotate that radius. Okay, so what we want to do is now we want to find a point on this circle such that the point from the circle to the directrix will also be 4.6. So if you were drawing this at home, you would take the string length, you draw the circle, then you'd pick up this string right here, you would have one end at the directrix and you'd move it upward and you would move this horizontally until the string hit the circle. So that's this line right here. So it's just way over there. So this line here you can turn on and off. So this distance here is 4.6. This distance here is 4.6. So if we move it, this S here is changing, is sliding this line back and forth. So if we move this over, okay, so this, it's not going to be exact, but this distance from the directrix to this circle here will be 4.6. And if we move this angle here, you can notice, so it's not going to be exact, but this point right here will be on the shape because the distance from this point to the focus is 4.6, and from this point to the directrix will also be 4.6. So if you're doing this at home, you would mark this point on your piece of paper. This wouldn't be the only point that you would mark. You would also move over here and you say, this point right here, would also be on our shape because the distance from this point to the directrix is 4.6 and from this point to our focus is 4.6. So you would mark this. And then what you would do is then you would take your string and you would either get a longer string or a shorter string and you would repeat this exercise, okay? Now we have a string that has a length of 5.4 and you would draw this circle. So this set of points are all the points that are 5.4 units away from the focus. You would then pick this string up and you would move it across this line until it hit the circle. So now this, it's not exact, but this point here will be on our shape. Again, because the distance, this is the distance from this point to the focus is 5.4, and the distance from this point to the directrix is 5.4. So let's actually do this. Let's build this shape. Okay. So what I've created in this animation are a set of movable points. So if you turn this on, there'll be all these points over here that are floating around. We're going to use these as our markers. Okay, so let's do it. Let's say that our radius here is at 4. No, notice that if we had a distance of like something smaller than this p-value, that there would be no point that would be a distance of 3.5 to the focus and then 3.5 to the directrix. It's too short in this case. Notice that you won't find a point that would match up. So we need a distance that's this value of p or bigger. So if we go to 4, and then we move this here, or let's just leave this up here. If we take this string here and we figure out where it hits the circle, it'll hit the circle here right at the origin, so that means that this point here will be on our shape, so we're just going to mark that. Okay. Let's do a different distance. Let's say, I don't know, maybe you get a little bit longer of a string and 4.5. So these are all the set of points that are 4.5 units away from the focus. Okay, you would grab this length right here and run it across to see where it hits the circle. So I guess also notice that when I change this radius here, that it's also changing this this vertical distance. Okay, so what we're doing 4.5. Okay, so let's move this over and see where it hits the circle. Okay, so this will be a point that's on our circle. Let's mark it here. Or this will be a point that will be on our shape. Again, because the distance from here to will be 4.5, and the distance from here to here would be 4.5. But that won't be the only one. We'd also find that this point here will also be on our shape. Okay, so these aren't exact, but we're just getting a rough idea of what this shape here would look like. So now we have 3 points on this shape. Okay, let's go to, I don't know, how about we go to, let's do 6. So let's go out, or how about we go out to 5? Sure. Okay, so we have a distance of 5. So this point here will be on our shape. And likewise, this point will also be on our shape. So we're just going to keep repeating this process. I don't know, let's go out to, I don't know, we could go out to 6. Okay. So this point will be on our shape. And this point over here will also be on our shape. Okay. I don't know, let's go out to, I don't know, how about we go to 8, let's say. Zoom out a little bit. Let's find a point on our shape. So it looks like here, here, and here. This is like great math research. We're brute forcing trying to figure out what this shape would look like. This is much more fun than me just kind of giving you the definition of the shape and just taking my word for it. Let's construct it. Okay, so these 2 points would be on our shape. We'll just keep doing this. I don't know, how about we go out to 10? You can slowly start to guess what the shape will be. So this point will be on our shape. And likewise, this point here will be on our shape. Okay. Let's go out to, I don't know, how about we go out to, 13. Okay. So this point will be on our shape. And this point over here will be on our shape. I don't know, let's go out to, we go out to maybe 15. Just keep doing this. This point will be on our shape. Just kind of roughly trying to find points. This point will be on our shape. So already we should be kind of noticing that our shape here will be kind of at least symmetric about this y-axis. Okay, I don't know, how about we go out to, let's go out to 20 now. Okay. This point will be on our shape. And over here, this point will be on our shape. I don't know, let's go out to maybe 25. We're already kind of starting to guess what the shape will be. Fun math discovery. Okay, this point will be on our shape. And this point here will be on our shape. I don't know, maybe let's go out to, well, maybe go out to 35. Let's go over here. This point will be on our shape. And this point over here will be on our shape. Look at this math research. Groundbreaking, groundbreaking. Okay, check it out. Okay, maybe let's kind of get rid of some of these features. Okay, let's get rid of this circle. Let's get rid of this line. Maybe you can kind of guess what shape this is. Does this look kind of familiar? I won't say it quite yet. Won't say it quite yet, but I hope you're I hope you're starting to see what shape it'll be. Let's do a little bit better with this animation. Okay, so instead of kind of plotting all these points right here, what I've done is this tab right here. If I open it up, let me kind of zoom in a little bit. This is going to tell you a distance from the focus to a point on our shape, and this other one right here will give a distance from the point on the shape to the directrix. So this length here is 5, this length here is 5, so that's saying that this point will be on our shape. And now I can control where these two lines are by using this N slider right here. So if I move back and forth, where these two lines intersect will be all of the points that will be on this shape, because all these points are equidistant from the focus, and then equidistant from that point to all of these points, the distance from here to here, from that point to the focus will be the same as from that point to the directrix. So these will be all of the points, but what I'll do is, notice that all of the points that we plotted are hitting these or hitting the intersection of this line. If you go down a little bit further, what I've done is I've made Desmos kind of actually, I don't know if you had like a nice marker right here, if you had like a marker attached right here, and you were to run this across, it would like trace out the shape. So I'll start here. So if you click on the graph button and we move it, it's going to trace out, that marker will trace out our shape. Trace out our shape. So maybe if I zoom out a little bit, maybe we can see a little bit better what this shape will be. Pretty cool. So we're tracing out this shape. Okay, can you guess what it is? Can you guess what it is? Okay, let's go down here and let's turn this off. And let's turn this one off too. Let's click on the shape. What is it? Here we go. Look at it. What is it? It's a parabola. Oh my goodness! How cool! How cool! This is, you probably never thought that this is the geometric definition of a parabola. What's true about a parabola, or the points on a parabola, is that the parabolas have these things called focuses and directrix, and the property of a parabola is that the distance on a parabola to the focus will be the same as the point on the parabola to its directrix. Pretty cool, pretty cool. Let's actually play around with some of these parameters. Let's get rid of these removable points here. So here is the shape. And let's see how this parabola here will change if we change the p-value. The shape of this parabola will actually be completely defined by how far apart the focus and the directrix will be. So let's go back up here to p. So notice here that if p is bigger, if we make the distance between the focus and the directrix larger, kind of zoom out a little bit, that widens the parabola. That widens the parabola. If we make the distance between the directrix and the focus smaller, that kind of scrunches the parabola together. It kind of, I don't know, makes it kind of skinny. So pretty wide parabola, I guess kind of a skinnier parabola. Now what happens if p is negative? If p is negative, what that does is that just makes the parabola, I guess, frowny face. So if p is positive, we have a happy face parabola. If p is negative, we get this frowny face parabola. But pretty cool. You probably never thought about a parabola having this geometric interpretation. So what we're going to do now is we're going to go to the whiteboard, and now that we have this geometric interpretation of a parabola, let's take this geometric interpretation and see if we can use it to define or derive the familiar equation of a parabola. We'll see you there. So we just discovered the geometrical definition of a parabola. You probably never thought of it like this, but what is a parabola? A parabola is defined to be the set of all points that are equidistant from a point F, called the focus, to a line L, called the directrix. Now what we want to do is, now that we have this geometrical definition of a parabola, we want to now derive its equation. Let's do it. Let's imagine as if, we were the first people to come across this geometrical definition of the parabola. Assume we know nothing about the parabola. All we have is this geometrical definition, and now we want to derive its equation. Let's draw a picture. Okay. Let's set up our axes. Okay, so here is y, and here is x. Okay, let's put our focus, let's say right here. So here's F. This is our focus. And we defined the distance from the origin to the focus to be the distance p. So the coordinates of the focus will be 0, p. We also have the directrix. Okay, the directrix. Okay. The distance from the origin to the directrix is also p. Okay, let's think about the equation of this line. This is a horizontal line, so it'll be y equaling to a constant. Okay, what will the constant be? Well, since we're at the origin and we moved down p units, this location right here on the y-axis will be negative p, so y will be equal to negative p, will be the equation of this horizontal line, the directrix. Let's draw our parabola. Something like this. Okay, this is the shape that we discovered. Let's now grab a point on our parabola. So let's maybe grab a point right here. Okay, this is supposed to be perfectly symmetric about the y-axis, but it's hand-drawn. Okay, let's grab a point on the parabola. Let's call it x and y. So if we drop this down, this is where x lives. This is where y lives. And what do we know about this point? Because it's on a parabola, we know that the distance from the focus to the point on the parabola will be the same as the distance from the point on the parabola to the directrix. So these lengths here will be equal. Okay, this would be the same if we were at another point. Let's say we had a different point here. Okay, the distance from the focus to the parabola, from the parabola to the directrix, these lengths here will also be equivalent. Okay, so let's try to come up with an equation for this parabola. Well, what do we know? What do we know? Well, in English, the definition says that the parabola is a set of all points that are equidistant from a point called the focus and a line L called the directrix. Okay, that's very Englishy, but now we want to turn it into mathish. In mathish, well, this length D1 will be equivalent to this length D2, so we're trying to get a little bit more mathy. So this just says in math that D1 in mathish, D1 is the same as D2. Okay, D1 is the same as D2. But we want to do a little bit better than this. We saw, at least from our animation, that really what defines a parabola is the value p. So when we're coming up with the equation, we would like to have x's, y's, and p's in it. So let's see how we could get those to show up. Well, let's write D1 and D2 a little bit nicer. Let's try to write D1 and D2 in terms of x, y, and p. Well, I think it's going to be easy for us to figure out what this distance D2 here should be. Well, notice that the distance from here, from the point on the parabola to the x-axis, well, that's the distance y. And the distance from the x-axis to the directrix, well, this is a distance p. This is a distance p. So we should have that D2 here should be y plus p. Okay. So we should have y plus p. Okay, what about D1? What can we do? Well, let's draw a right triangle. Maybe in blue. Look at this beautiful right triangle that we can create. Okay, so maybe I'll draw this triangle over here. our picture's not so crowded. So we have this triangle right here, right triangle. Okay, this is D1. So to figure out what D1 is, we're going to try to use the Pythagorean theorem. So we just need to know what the length of the two legs are. Okay, let's think about what the length of the horizontal leg will be. So we want to know what this physical distance from here to here will be. And well, I hope you believe that the distance from here to here will just be x. This will just be x. Okay. Well, now what'll be this vertical? What'll be the length of this vertical leg? Okay. So we want to know what this distance here is. Well, from our picture, let's see. Well, I know the length from the x-axis to this point will be y, but the length from the x-axis to this bottom point right here, well, that'll be p. The distance from here to here, this distance here is p. So this length here must be y take away p. So this is y take away p. Y take away p. Okay, well now if we want to know what the distance is, we'll just use the Pythagorean theorem. What's the Pythagorean theorem say? It says that the square of the hypotenuse is equal to the sum of the square of the legs. Okay, but we just want to know what D1 is, so we'll square root both sides. So D1 will be equal to the square root of x squared plus y minus p squared. And that's what we're going to put right here. So we have the square root of x squared plus y minus p squared. Okay, and here we have it. Here we have the definition of a parabola in Mathish. In English, the definition of a parabola is a set of all points that are equidistant from a point called the focus and a line called the directrix. But in Mathish, that says, in a mouthful, it's the same thing as saying, well, the square root of the quantity x squared plus the quantity y minus p squared is equal to y plus p. I don't know. In Mathish, it's a lot. But this is the definition. This is the definition of a parabola written in Mathish. Okay, but I could say, hey, we've done it. Hey, this is the equation for a parabola. But I mean, come on, how ugly is this? How ugly is this? Let's massage it. Let's massage this thing. Let's make it look pretty. And I know in the past we might have a feeling to, I don't know, we might kind of know what a parabola looks like. So we're kind of at least expecting something familiar, and this doesn't look super familiar to me. Okay, let's write this up a little bit higher. So we discovered that in Mathish, the definition of a parabola is the square root of x squared plus y minus p squared is equal to y plus p. Okay, let's clean this up. Let's massage it. All right. Okay, what's hurting my eyes when I look at this? What's hurting my eyes? Ow, that square root. Ow. Ow, don't look straight at the square root. Get rid of it. Don't look at it. Just square it. Square it with a better marker. With a blue marker. Square it with a blue one. Okay. We'll square both sides, and then I'll get rid of the square root. Get rid of that eyesore. X squared plus y minus p squared will be equal to y plus p quantity squared. Okay, my eyes are a little bit at ease. Okay, what to do from here? What else can we do? Okay, what's screaming at me to do here is to foil these. Let's expand. Well, why would we want to expand? Well, notice here that if I were to expand this, I'd get at least the first term would be a y squared. I'm going to get another y squared over here, and I could cancel those out. So I think expanding is going to help us here. So let's do it. Let's maybe write this in a black marker. So what are we going to get? We're going to get the x squared plus, this will expand to be a y squared minus a 2py. This comes from the O and the I in FOIL. And I'll get a negative p times a negative p. We'll get a p squared. And that'll be equal to, over here, we're going to get a y squared plus, we'll get a 2yp from the O and ion foil, plus a p squared. Okay, now we can start canceling. We could subtract y squared from both sides. Okay, those will go away. Ah! Subtract p squared from both sides. Oh, this is cleaning up nicely. What do we have left? We have an x squared minus a 2py is just going to be equal to a 2yp. Let's just change the order of multiplication. Make that a 2py. Okay, now let's add 2py to both sides. Okay, so we'll have that x squared. We have 2py plus another 2py, so we have 4py's. And here we have it. And here we have it. This is the equation of a parabola. This might look a little funky to you. You know, hopefully we're familiar with parabolas being something of the form y equals x squared. Well, if we divide both sides by 4p, or how about instead of dividing both sides by 4p, we could equivalently multiply both sides by 1 over 4p. So that'll say that y is equivalent to 1 over 4p times x squared. Well, 1 over 4p, for, if p is a fixed number, you tell me the distance between the focus and the directrix, and you have a unique parabola. This is just some sort of constant for a fixed p. So let's just say that this 1 over 4p, let's just say it's some number, we'll call it a. So this is saying that y is equal to ax squared, which is something that should be fairly familiar to us. This is like a parabola. This is a parabola if a is 1. If a is 1, this is just y equals x squared. This is a parabola where its vertex is at the origin. And that's what we saw. Now, what is this a doing? Well, what is this a doing? Well, let's think about this. Well, what happens if p gets bigger? If p gets bigger, we're going to have 1. We're going to have 1 over a fairly big number. A will be getting closer to 0, to 0. So that just means as p is getting really big, just a is getting smaller. So it's almost like we'd be multiplying x squared by a small number, which would be in a fraction. That should kind of condense. That should condense my parabola. And that's exactly kind of what we saw in the animation. As p got larger, the parabola kind of opened up. But you can kind of think of that almost as squashing the parabola. It's kind of squashing the parabola. It's kind of opening up. So as p gets larger, a gets smaller. That's saying that this is a parabola that's opening up, just like we expect. Well, what if p is getting smaller? If p gets smaller, okay, I have 1 over a really small number. That means that this number here is going to get larger. So as p gets smaller, as we move the distance between the focus and the directrix closer to one another, what did we see in the animation? The parabola was kind of closing in. It was getting kind of skinnier. Well, if p is getting smaller, a is getting bigger, that means I'd be multiplying x squared by a large number. That's going to be stretching the parabola. And that's exactly kind of what we saw in the animation. The parabola is getting stretched. So this is all agreeing with everything that we know about parabolas, which is beautiful. Okay. I guess notice also in this case, if p is positive, if p is greater than 0, that means that the focus is above the directrix. Well, then a would also be positive. If a is positive, we have a smiley face parabola. If p is negative, that's what we saw in the animation where the focus was below the directrix. If p is negative, well then a is also negative, and we're going to have a frowny face parabola. This is beautiful. So it's great. It's great that we have this geometrical definition of a parabola, and just with a little bit of, a little diagram, a little spice of Pythagorean theorem, we were able to come up with the equation of a parabola. Now, when we ever are thinking about the equation of a parabola in its geometric form, with its geometric definition, we normally just write x squared is equal to 4py. And for when we're working with conics, or when we're working in section 11.1, this is the version of the parabola that we're going to use. In the next video, we're going to be doing a lot of practice with working with this version of the equation of a parabola. We'll see you there. Take care.